Evening. Hi, Paz. How are you doing? How's it like? It's just you and I alone today.
Yeah, it looks so.
All right. Mikey did send a message to say that he has a challenge. So I think we should go. I think we should go and we should start. Um
Oh, Michael just log in. Is what is Asia just log in.
Even,
oh
even.
so I'm meeting my way upon.
As you talk, sir.
Mm,
Good evening,
good night.
afternoon.
Good night, Miss Asia. It's not no, this is not I don't want Michael to tell Paz Michael, I mean Paz. It's not at 6 o'clock. This a night. Look how long the eye away upon you. Well, me hear from Mikey. Look how long me away upon you, Asia. Well,
Sir, me
Carol there.
just step in. I still have more clothes, sir. You know me
Yeah.
feel.
Never mind. The struggle is real. But no, why Paz was laughing is that I just said to them that Paz is me and you alone. Come, make us start. And just as I said that, both of you logged in at the same time. But anyway, Mikey, your message was well received, and I hope that things will work out for the good.
Man, thanks
All right,
much.
Asia. Yeah, man. Asia, I'm gonna give you 4 more minutes just to go sort out yourself. Wash your hand and grab a juice and come. 4 minutes. I'll come back.
Thank you, sir. Much obliged.
Good. Thank you.
Oh, sir, you know, I realize, you see, once you understand like exactly how many electrons are in the valence shell,
Yes, sir.
it easy for you to write the formulas.
Oh, absolutely. But I think
You
I
know,
said that. Yeah, but I think over this weekend I'm going to give you that assignment because
oh,
it is
wow.
it makes life so much easier.
Yeah, man, it make it easy, man.
Yeah, man. Just to know the periodic table. You know, it is what is used to soften things, and once it is that you know it, you should be good to go. Let me just while Asia finds her way, let me just present share something with you just to support the point that you are making. Um, so we're looking at these charges for argument's sake. So I did say to you that the sulfate is SO42 minus. So when you're writing hydrochloric acid, when you're writing sulfuric acid, and you're writing sulfuric acid, it's going to be H2SO4. And didn't plan to write, so they're not just yet. So I'm going to put my writing tablet. So just give me half a second. Let me just pull it grab these to demonstrate something here. There it goes. So what I was suggesting to you the last time is hydrogen has a +1 charge. The SO4 has a 2 minus charge. So when we're doing our cross multiplication, it's going to be, we don't carry the charge, so it's going to say H2SO4, and really it's to the first, but because it's 1, we just write H2SO4. So that's the formula for the sulfuric acid. So you have some common charges that we have to know. So the chlorine is Cl minus, we know this. Bromine Br minus, iodine I minus, and fluorine F minus. We know this from previous sessions because we've written sodium chloride before. Sodium chloride is pretty similar to sodium bromide. We've looked at potassium iodide as it relates to that experiment we did with the yellow crystals, or sodium hydroxide. So this is a hydroxide ion, OH minus. The permanganate or the manganate 7 MnO4 minus. So the potassium permanganate is KMnO7, MnO4. That's a potassium permanganate 7. That's the purple stuff. The hydrogen carbonate is HCO3 minus. So like sodium hydrogen carbonate for argument's sake. Sodium hydrogen carbonate is going to be Na8CO3. The ethanoate is from our acetic acid. The vinegar that we use in the kitchen, CH3COOH, that's an organic compound. So to show you that sometimes we use these acids, and it's proof here, because when we're doing our vinaigrette on a nice garden salad and you put your vinaigrette on it, man, it stay good. It got on nice. It's really acetic acid. It's really the ethanoate that we are using, right? When you're doing a sweet and sour, you want a tangy taste, so you put a little vinegar there. When we washing our meats, we use the vinegar. So it is good. And then we have the methanoate. These are organic compounds. We have the methanoate, the HCOO minus. And those are the +1 charges. Then we move over to the +2 charges. The sulfate we talk about. The carbonate, CO3. So like sodium carbonate. We wrote sodium carbonate the other day in class. Sodium carbonate is Na2CO3. And how did we get the Na2CO3? Because sodium is Na+1, and the carbonate is CO3 2 minus. See here? CO3 2 minus. So when we do the cross multiplication now, we're going to get Na2CO3. So it is important, because I'm suspecting that you may get formula writing on the exam paper. They may give you an equation, something similar to what we're doing now, and you're going to be writing your formulas. Well, a little bit more than formulas, your balanced equation, right? Your sulfide, you can have your sodium hydrogen sulfide, your chromate, dichromate, your ethanoate, or your ethandiolate. You have the phosphate. Your phosphate is what is often found in your fertilizers. That's a source of the phosphorus. We talk about NPK, and we talk about the nitrite. And then now, those are our anions. Remember, the anions are the ones that are negatively charged. See, -1, -2, -3. And then we look at our cations now. We met these: lithium, sodium, potassium, the Na+, the group 1 metals. The group 2 metals are the ones that have 2 valence electrons. So you see, it supports the point you're talking about, Mikey. The valence electrons.
Yeah, definitely.
Right. So the group 2 metals, you're talking about the sodium, calcium, and the barium. All have 2 electrons in its outer shell, right? And then of course we talk about the aluminum, Al3+, iron 3, Fe3+. You have a chromium 3 as well. Now this one is transition, and then now we're going to other things now, or lead or iron or zinc or tin or copper. These are all 2+ charges, right? So like lead nitrate is going to be Pb, the nitrate is NO3. I don't have the NO3 up here, but yeah, so you can have your lead nitrate being formed. You have a tin, you have a copper. So you have the copper 1 and you have the copper 2+, right? And we'll speak about these things, in terms of, the transition metal, you have different states of it. So this is why you find these variation in the stuff. And of course, our hydrogen here, which is our +1. We made the ammonium ion already, NH4, because we did write the formation for the ammonium chloride. So yeah, so these are things that we must know in order to write our equations. One of them you're going to be looking at today. Yeah, the same carbonate here, right? Carbonate. Because when we react an acid with a carbonate, we will always get off carbon dioxide, the salt, and water. So for our last, Asia, are you back?
Yes, sir, here.
Okay, good. So during our last session, we spoke about certain reactivities. So we're looking at the acid base, and if you follow the outline with me, we're looking at and incidentally we're moving a little slow. But anyhow, I think I'll be able to catch up when I move into the spheres. Because you are going to be doing lots of reading on your own for me. This part, as I explained to you, is going to be dependent upon me to explain the foundations of chemistry. And then we get into the specificity of it, where you will read and we'll have conversations. So whenever I react an acid with a base, or an acid with an alkali, one of the things we say that all bases are alkali, but not all alkali bases. And we can get into that conversation, or maybe don't get into it because it is going to be too much into the chemistry. But generally, an acid plus a base will give you salt and water only. You only have salt and water coming off when you react an acid with a base. And one such acid could be hydrochloric acid plus sodium hydroxide. And what you're going to be getting is sodium chloride and water, NaCl plus H2O. So these formulations you must know. If I react on an acid with a metal, I am going to get a salt that is formed. But what is going to come up is hydrogen gas. So if I react any of these metals, sodium, lithium, potassium, magnesium, calcium, barium, lead, iron, zinc, copper, tin, silver, ammonium, I am going to get off the salt plus hydrogen gas. Hydrogen gas is going to come up. I know one of the things that we do confirmatory tests inside the laboratory so that we can say, oh, boom, this is for sure. So the hydrogen gas, it extinguishes a glowing splint, for argument's sake, and the oxygen gas rekindles a glowing splint, and the carbon dioxide gas that comes off, we run the gas through calcium hydroxide, aka lime water, and the precipitate, it forms a white cloudy precipitate. We know that's a positive confirmatory test for carbon dioxide. So those are some reactions that we must know. We must know that an acid plus a base gives me salt and water only. You must know that an acid plus a metal will give you salt and hydrogen gas. You also must know that when I react an acid with a carbonate, I'm going to get the salt that is formed. I'm going to get carbon dioxide that is coming off, and I'm also going to get in water. Then how, sir, you know when you react a carbonate? When you react an acid with a carbonate, you're going to be seeing this rapid effervescence, rapid bubbling up. Hello, when you see things are bubbling up, you just put a thumb over that test tube, for argument's sake, to trap the gas inside. Now, sometimes the rapid effervescence kind of pushing the gas, away from your thumb. And think of you having a bottle of soda, and you shake it up, and you're trying to put your thumb there. Sometimes the pressure that is built up in the bottle is actually pushing your thumb away, and you can't hold it any longer. Anybody ever tried that yet?
No, sir.
Okay. Wait, Mikey, when next you into this? Don't try to turn it, right, Mikey?
Yeah, man.
Yeah, man.
And
So,
it starts pre-out, even when you do it with champagne.
All when you try to hold it, even when you put two thumbs or you put the whole hand to cover it, the pressure that is built up is so great that it's a losing battle. So sometimes when that happens, if we suspect that we're going to be having this the production of carbon dioxide, we will have a sample of our calcium hydroxide already on hand. So that as soon as the gas is produced, we just open the mouth of the test tube and allow the gas to run into or to float into another test tube, and then we invert the solution. Once we see a white precipitate formed, we know that's a confirmatory test for carbon dioxide, right? We're not supposed to inhale it because it cannot be out. You understand? So those are some of the things that we must know. But yes, these are things that come in handy, especially when it is that we are writing our formulas. All right. So we are going to be going back to to doing our calculations. And we had our conversation regarding our sodium hydroxide, or calcium, or conversation about balancing that equation, and the reaction that we're using is sodium hydroxide with our sulfuric acid. And of course, these are both dilute, they are aqueous solutions. And the salt that is formed, let me just to show you, just to show you that that's the base plus the acid is going to give me a salt. And water. Always. Always. All right. Now, we also looked at the mole ratio, and we recognize that based on this balance equation, I needed 2 moles of sodium right here. I needed 2 moles of sodium so that I will have the same number of moles of sodium on one side to the same number of moles of sodium on the other side. My sulfate ion, SO42 minus, will give me 4 oxygens, 1 sulfur. I have 1 sulfur, I have the 4 oxygens, but if I look over here, so I had one more oxygen, but here, so I had 1 more oxygen. But the mere fact that I needed to get 2 sodiums, and I put the 2 here, this 1 oxygen changed from 1 to now 2. So was this hydrogen changed from 1 to 2? So now I have 2 hydrogens from here and another 2 hydrogens. So I have 4 hydrogens on this side. So therefore, in order for me to get my 4 hydrogens, I had to multiply this and give me 2 moles of water. And then in doing that, I recognize that my equation is now balanced. So I'm going to have a 2-to-1 mole ratio. 2 moles of the base was required to neutralize 1 mole of the acid. Any questions from that so far? That was a recap.
No question.
Yes,
but sorry.
Go ahead.
Based on what you are saying, every reaction gives salt.
Yes, you get a salt.
The only difference is whether it's a base, an acid, or a metal, which would either give you hydrogen gas or hydrogen gas, carbon dioxide, water, and salt.
Right. Right. So you have to know which is which. Correct. So you have to know which is which. Yeah. Question?
No question. No question.
Okay. One may say, why the importance of all of this, sir? No, you see, when I tell you, we're going to have to start reading. Come next week, I'm not going to be on this, because I'm trying to finish off this thing as quickly as possible. Because come next week, we're going to talk about things like acid rain. What is acid rain? Name me. And acid rain is a pollutant. It is an atmospheric pollutant, and it is formed pretty much by a buildup of some gases in the atmosphere. It's a buildup of some gases in the atmosphere. And the buildup of these gases in the atmosphere, a weak sulfurous acid is formed. And the sulfurous acid come from different sources, motor vehicles, so forth and so on. And these dangerous gases just lurk around in the atmosphere. It lurks around in the atmosphere. When it rains, it forms the weak sulfurous acid. And also the weak carbonic acid, because they have too much carbon dioxide up there too. So we have the carbonic acid that's being formed. And the truth of the matter is, you know, in our times past, you know, people using their umbrellas in some places, after a while, holes start to develop in the umbrella because the acid eating out the umbrella. And the whole stuff. So these are things that we need to know. Why we're studying this and why we need the formula writing, because when you're doing your explanation to me about these atmospheric pollutants, you must give me formulation. You must give me balance equations and tell me what is happening and how this works and how that works. These balance equations, including state symbol. All right. So this is the importance of what it is that we're doing. Any questions on that before I continue?
No. Not for
Okay.
me.
All right.
No
Okay.
questions, sir.
All right. So now that I have found my balance equation and I have my mole ratio, I'm going to calculate the number of moles in my known substance. So remember, you know, what is my known? Hold on a minute, please. All right, sorry about that here, guys. Getting very nasal, so I had to try some of this silly nasal drop. Make sure you take the vitamin C here because something is just going around. And
zinc, not just the vitamin C, zinc as well.
yeah, man. So I do a combination of those, zinc from my Bico zinc, vitamin C, and zinc together. I was just before class, preparing for your class, I was just scrolling through TikTok again, and saw where there is another incident with aircraft, but in Atlanta this time, where the passengers had to vacate the aircraft because of a failing engine and it was smoking and, you know, the fear of it exploding. And I'm saying to myself, enough already. Since 2025, enough. All right?
Yes, sir. When I think it's maintenance issue anymore.
I don't think so. It has to be something more than that because of the frequency with which the occurrences. It is scary. It is frightening. And if I would want to take on something that somebody said, turn on your yard. Because I mean, air traffic is no fun anymore. Go ahead, Paz.
The only good thing about this is that the air prices them are drop.
Yeah, but
so you can always take your flight.
Yeah, but you see, maybe that is a ploy to catch me. Come take my 3 points.
Sir, you see from the military helicopter turn into the American airline.
Literally turn into it. Literally.
Yeah. When I saw the radar information, I said, but why on earth?
You remember helicopter can maneuver better than an aircraft, you know.
Exactly.
So he's the one that's supposed to say, oh, oopsie daisy, I'm too close. You're telling me saying I realize he's so close to them?
A man could have stopped and bust a reverse. Easy.
Straight.
And the man fly right in at the plane.
Right? And just take out so much people. It was what, 64?
Yeah.
it is crazy. And then one after the other one this week.
Something happening in South Korea too.
Same
Yeah,
thing.
man. Some
Yeah.
some
Just a
cyber
while
attack
ago.
or something, man. This
Today or
are
yesterday.
this are more than pilot error.
Maintenance. Oh yeah. Oh,
Yeah.
absolutely. I mean, I was while we're waiting on you and Asia, Mikey. I saw it as like, what on earth is happening? Like seriously? No, remember, the people them on the tarmac. Well, it wasn't really tarmac. This was covered with snow, and of course, just imagine, me dying in an aircraft explosion, and trust me, those jet fuel very explosive, because it's light. You remember, you can't use heavy fluid there, and it's very light. You understand? And the man them run, and and people got injured in the process, right? Because I don't even think the slides were out, so people were jumping from the aircraft. I don't know. Only Jesus alone can give us a soothing spirit, because it is very unsettling what is happening now. But anyhow, it is what it is. Um, it is what it is. All right. So what we need to do, so our known was the sulfuric acid, because it says 25 centimeters cube of a 0.25 mole per dm cube sulfuric acid. So the known was sulfuric acid. And so because the known is sulfuric acid, I'm going to be using the known to calculate the unknown. So guess what? It says here that it is 25 live 0.25 moles per dm cube sulfuric acid. 1 dm cube is equal to what? Centimeters cube. Hmm?
100.
A little bit more than that.
1,000.
1,000. All
D,
right.
sir, what is the D?
All right. So remember,
Oh,
he,
the mole
That's
mole
our
per
decimeter.
Mr. Don't commit murder.
Decimeter.
Millimeter, centimeter, decameter, meter,
Deca. Yeah.
right? Echo and kilo. Right. So it is a form of, again, representation of liquid volume. All right.
Okay. Okay.
All right, good. So 1 dm cube is going to be equal to 1,000 centimeters cube. So what I'm saying to you, in every 1,000 centimeters cube, I have 0.25 moles. I have 0.25 moles. So when I'm making up a solution, the solution is made up in a volumetric flask. Now I have different types of volumetric flasks, just like I have different types of pipettes. So I have a 1,000 centimeters cube or 1 dm cube volumetric flask. I have a 1,500. I have a 2,000 volumetric flask, and they're also called a round bottom flask, because I mix the water with the acid properly and then fill it up, and then I get my diluted solution. But I have to be very careful, because the amount of heat that is generated when I add water to the acid. I have to be very careful by putting some water in the volumetric flask first, and then I take my time to add the concentrated acid in there, so that at least I don't cause an explosion, because the heat that is generated can actually burst that volumetric flask. And think of you standing in your kitchen cupboard now, or your bathroom cupboard. Where does the counter catch you? Just think about it. When you stand in your kitchen or your bathroom, where does that cupboard catches you on your person?
Right,
Sure.
right a little bit below our right in your waistline, basically.
Oh, the height.
Yeah, where catch you, pals?
It's not at my waist, but lower.
Yeah,
Okay.
look it's below, yeah.
Yeah.
Asia, where catches you?
Her shoulder. No, that I carry.
Bright boy shoulder. No, that's short. Like, like waist height,
Okay. All right.
or a
Now,
little bit below the waist.
what is, you know what is below, a little bit below the waist, don't it?
Yes, sir.
Frontal view, right? So you see what is going to get damaged, don't it? Right. So we have to be very careful when we're making up these solutions in the laboratory. We have to be very, very careful because we don't want to potentially hurt ourselves, and whether or not it's just that private part that is going to get damaged, but any part of our body would scar us for life. All right. So one has to be very careful. So I'm going to calculate the number of moles in my known. I'm calculating the number of moles. So I'm saying 1,000 centimeters cube of my sulfuric acid contains 0.25 moles. It contains 0.25. So every time you see something like this, 0.25 moles per dm cube, it is telling you that you have 0.25 moles in every 1,000 centimeters cube of solution that is made up, right? So what I'm saying to you now, of that 1,000, so I know that in that 1,000 centimeters cube, it's containing 0.25 moles. I want to find out how much of that 1,000 that was used. So I'm saying now, 1,000 centimeters cube of sulfuric acid contains 0.25 moles. So therefore, 23.50 of the said solution is going to contain 25, nope, 0.25 moles times my 23.50 centimeters cube divided by 1,000 centimeters cube. The centimeters cube is cancel out. Tell me what you get when you do that calculation, please.
Uh, 0.005875.
Yeah, 0.005875.
All right, thanks for confirming. All right. No, is that more or less than what we started off with?
It looked like less because you move like two additional decimal places.
Yeah, but if you look at it, do you expect that we're supposed to get less? In 1,000 centimeters cube, how many moles we had in 1,000 centimeters cube?
Point
0.25.
0.25. And how many?
Yeah.
What amount of the 0.2? What amount of the 1,000 were we using? $23.5.
Yeah.
23.5. Yeah.
So the 23.5 is only a fraction of that 1,000.
Okay.
So put it this way. When I'm craving enough to drink a Dr. Pepper, and it says to me that it has 150 calories, but the serving size is 1 can. And this is 150%, this is 150 calories of my daily percentage value. If my daily value of calorie intake is 300, and I've already had 1 can of Dr. Pepper, how much more can I take in to fit my daily value?
The one more can.
One more can. And if it so therefore, so this is why I'm not sure how many of you would have seen this, but this is why, you know, in the mornings when people go like to Starbucks, you see they have their app out and they're saying, and what Starbucks does know, well, I mean, they have to do the
They put
places,
up
you know,
the amount of calorie in
they
each.
have to put the amount of calorie in each of the stuff. Yeah. So when
Yeah,
you
because
go,
I want a lawsuit, but that's why.
absolutely. So when you go to what them call himself again, Subway for argument's sake, and you want a BLT, and you look at the BLT and you say, okay, I think I should have a 6-inch. Nah, I'm hungry. I want a foot long. But the foot long is going to surpass your daily calorie intake. And because you're on a strict diet, it could that you're diabetic, or it is that you're on a strict regime to lose weight, or you're a fitness guru. You say to yourself that, yo, I can't have a foot long. I have to have a 6-inch because this morning I had coffee and coffee was this amount. So people literally, there are apps out there that you can download on your phone and to track what it is that you have. And once it is that you've reached your daily limit, it's done. Then, sir, it is now 12 o'clock and I've had my daily calorie intake. What do you do? Drink water. Drink water, or you have fruits. So those
Or
are
eat
natural,
cabbage.
yeah, right?
Cabbage as your calories.
Or substitute that meal with vegetables, right? So you can have vegetables without any sauce on it, you know, no vinaigrette and no mustard and no Thousand Island, none of those, you know, because those contain calories. So for your dinner, what it is that you can have is raw veg or some okras, and you have water because you've already taken your daily intake. So you can't take anything else. So, you know, but in this part of the world, though, that Jamaica, we know do them something there. I'm going to tell you why we don't do that. Because, and if any of you call me Craven, well, actually, the Craven one is not here. Instead, I'm a little worried about Carol. I know she has this thing about her. Sometimes she just disappear upon me, you know. But anyhow, when you buy your water crackers, how many water crackers is considered a serving?
I think them's about 4 or 5.
Really?
Yeah, I think I that the last time we checked.
Anybody have any water crackers, the small water crackers in them cupboard? They can look at it, please.
So it says 3, 4, or 5 crackers.
What did it say?
So 4, 4.
It says 4.
Mm-hmm.
Which one of them are you using? The cinnamon or the regular one?
The regular.
Oh, I don't know why
4
the last.
water
I don't. And
crackers per serving.
is it tough crackers or the soft one?
Water crackers, tough crackers,
The tough one.
Excelsior, fat free.
Okay. All right. Okay. So I stand corrected then. I thought it was 3. So it's 4. But let me tell you something. You see, when I eat water crackers, all one doesn't I eat.
So now I never have to
It's
hold
all
the bag.
sweet and all.
Asia, you can't say them things that may pass here, you know, because I'm gonna trouble you, you know, Asia. No, but it's true, Asia. And guess what? You see, all you can have a piece of cheese with that. Me a go on and I go on and if you know say the bag done, me a feel for more. Me recognize it done. Come in if you didn't know say the last one I did upon. So I say this to say to you that oftentimes we are not even mindful of what it is that we're doing. All right? No, it's the same thing. Well, I don't care who wants it. Carol is not here. Leave Carol alone. If we have to be very mindful of what our intake is. The same thing I'm saying to you. So just like when you have one whole bag of water crackers, and the small water crackers, I think 20 water crackers come into that bag. 20. So if it is 4 servings, if it is 4 water cracker per serving, it means that it's a 5 serving bag you buy. And sometimes a one go, you don't want back. So it's 5 servings you're having. So what I'm saying to you is that when I pull out 1 serving, it simply means that I'm going to have only 4 servings left. Are you following what I'm saying?
So the serving is just a suggestion.
It's only a suggestion, but guess what? Because it is not Prizac. Because when they're saying to you that this is 150, chances are it could be 149 and something, or maybe 148, and then those start say them going put on something. All right, so I'm looking at a snack here. Rockstone. Like seriously? I'm looking at a snack. This one is Thunder Paws, Bigfoot Thunder Paws. And the Thunder Paws is 140 calories per serving, per package. So if you have a Thunder Paw and a Dr. Pepper, that's almost 300 calories. You can't have not more of that for the day. So, you know, one has to be very careful in what it is. So this is exactly what is happening here.
Sure.
Yes, Papa.
So what they call empty calories.
Empty calories. Okay, so some of them, you have good ones and you have bad ones. So the good one, they call the empty one. The bad one is what we call is the one that you have to be careful of. You follow what I'm saying? So the good one would be like, you know, you're eating your fruits that naturally contain sugar. So you don't have to use any liquid sweetener. You don't have to drink soda and juices and something there. You have an orange, it contains enough sugar that can keep you. You have a banana, you have a watermelon, so forth and so on. You follow me?
Yeah, because when I heard empty calories, I thought that you wouldn't put on weight. It's just empty calories. So.
No, sir. Don't make them fool you here. don't make them fool you.
So, sir, I'll even know when all the GMO adding sugars and such is okay again.
Oh, absolutely.
Like apples and so sweeter.
Oh, absolutely. And those are really not good for us because you know, it is, as I said, GMO, it is genetically modified. And but me not lie you do. When I catch a foreign, you see, and I catch a Costco or BJ's or even Walmart too, and I buy one of them $5 watermelon day, I would just sit down and eat that the whole day. Nice eye.
That is sweet.
Oh, Jesus, Father. Last time I bought it, my mom was like, oh, why are you buying such a big watermelon? You're not going to eat it up and and I said, don't worry about it. It won't waste. But you're not going to be here long enough when you're going back to Jamaica. And then I say, don't worry about it. It's fine. So then I drop that in the sink and I wash off that. And I go on it and I bust that in two. She alone eat off quarter. Oh, this is so nice. I say, yeah, right. And by time before the night is out, half of the watermelon is devoured. By the following morning, the following afternoon, there was no watermelon left. It's like we never bought any. Watermelon, nice, man. So yes, Asia, you know, sometimes you have to be very careful because we do genetically modified foods, and because of the demand, you know, we can't wait until the gestation period for it. So we genetically modify it, so it is that we can grow it faster. And you know, really and truly, sometimes it won't even add anything. Case in point, I had a naseberry this morning, and I was like, "Oh Jesus, it's long time I don't have the naseberry." And you know, this one wasn't fully ripe, but it was ripe. And I washed it, and I say, you know what, you know, it's the first one for the season. Let me not eat the skin. Let me just go and have the fruit. So I opened it and I started eating, and it was so fresh. And I know what that is. It means that it was picked young, so it's not fully developed, and then it was force-ripe. And these things don't add nutrients to your system. These things cause illnesses on your body because we're eating foods that not ready for consumption, you know? So anyhow, So the point is taken that in my 1,000 centimeters cube, I have 25. In my bag of water crackers, I have 5 servings. And of the 5 servings, they're only taking out 1. That means I have 4 servings left. So I'm only concerned with my servings. See, I want to find out how many moles are contained in my 23.5 centimeters cube. And I've just calculated it. 0.005875 moles contained in my sodium hydroxide rubbishness, my sulfuric acid, contained in my sulfuric acid. Now watch me. I'm going to say to you, from the balance equation, two moles of my sodium hydroxide reacted with 1 mole of my sulfuric acid. Now, if the number of moles of my sulfuric acid is 0.005875, it means then that what am I supposed to have here? So, how many number of moles reacted in the sodium hydroxide?
2.
2 times
Times.
more, don't it?
Yeah. So you're gonna multiply that by the amount and to get the amount of sodium hydroxide that was reacted.
Right. So tell me what that is.
Where? Zero 0.01175.
Somebody confirm for me, please.
Yeah, 0.01175.
All right. Yes. Very good. So I know how many moles now of sodium hydroxide I have. So having now I know the number of moles of sodium hydroxide, I can then go ahead and calculate the concentration. So I know that in my 25 centimeters cube of sodium hydroxide that I pipetted, it contains 0.01175 moles. What if I want to calculate the concentration? How concentrated was this 25 centimeters cube? I can now say the concentration. I can now say 25 centimeters cube of sodium hydroxide contain so therefore 1,000 centimeters cube of NaOH will contain the 0.001, nope, 10, 0.01175 moles times 1,000 centimeters cube all over 25 centimeters cube. Multiply 0.01175 by 40 and tell me what you get, please. .4 or 0.4 what?
0.47.
0.47. So I'm going to get 0.47 moles per dm cube. So that is going to be the concentration of the sodium hydroxide. So the concentration of the
Sir,
sodium
hold
hydroxide,
on,
yes,
sir. Why we multiply it by 40?
because it's really, okay, multiply 0.01175 times 1,000 times 1,000 divided by 25 and tell me what you get.
Oh, yeah,
So 25,
0.47.
right, so 25 into 1,000 is 40. So I saw that, that's why I said times by 40. So I put
Okay,
that in.
I was like, but then
Right.
when I yeah, all right, no problem.
So what it is that we've done here now is to calculate the concentration. How concentrated is the 25 centimeters cube of the sodium hydroxide that we pipetted for that reaction? So I can now say to you, for argument's sake, if I wanted to find that neutralization to make a bar of soap, I now need that, I now know that I'm going to need a 0.475 moles per dm cube of the sodium hydroxide. So I just make up that. So what that says to me now is that I just go ahead and just make up that solution. I know how to make up the 0.475 solution of the sodium hydroxide because I've done my neutralization. And this is going to tell me this is exactly the amount of stuff that I need to make. It's like a recipe. It's like a recipe. I want to make 5 cookies, and the book tells me that, yo, to make 5 cookies, I'm going to need 1 cup of flour. I'm going to need a tablespoon of this. I'm going to need 2 of that. I'm going to need 3 of that. I'm going to need that of that. But what if it is asking me to make 7 cookies? I can't go make double the ingredients and just make 10 and then eat off 3 of the cookies and then just give them 7. No. At some point in time, I'm going to be running into my profit. Right? I'm going to run into my profit. So if the customer wants 7, a 7 I'm going to make. I'm going to rescale my ingredients in order to get the 7. So if it is that you're making aspirin, or if it is that you're doing a bar soap or anything, and you know that the concentration of the sodium hydroxide that you need now is going to be 0.47, you go ahead and use the 0.47, make up the solution to be exactly 0.47. And there are ways you can use to make it up, because I mean, you do the calculation, the mass of it over the relative molecular mass will give you so concentration is going to be equals to the mass in grams over the relative molecular mass. So the relative molecular mass is going to be the mass of the atom. So the relative molecular mass of sodium hydroxide is going to be 23 plus 16 plus 1. Where did I get the 23, the 16, and the 1 from? When I speak about 23 with sodium, what am I talking about?
Repeat the question, sir.
When I speak of sodium with 23, what am I referencing?
The amount of 23, the mass number,
When I speak of 16 with oxygen, what am I referencing?
the mass number.
Good. So that's the relative molecular mass of the compound. So I'm looking at the relative molecular mass. It's going to be 23 and 16, that's 39. So it's going to be 40 grams per mole. It's going to be 40. And if I know the concentration to be 0.47, and I multiply that by 40, I'll get the mass in grams of the sodium hydroxide that I need to use. Remember, sodium hydroxide comes as a pellet, you know. It's a sodium hydroxide pellets that it is. So I'm going to dissolve those pellets now. So what I'm going to do is to measure out those pellets. So when I do that calculation, it tells me how many grams of the sodium hydroxide that I must have. I just go into the balance room, measure the amount of pellets, and then now I am going to be dissolved, the amount of pellets that I've made up, I'm going to pour those pellets in a volumetric flask, a 1,000 centimeters cube volumetric flask, and I'm going to dissolve, and I'm going to make it up to 1,000 centimeters cube of water, of liquid. And then that would be that would give me my concentration of my 0.475. So it is easy to make up the solution. So what it is that I'm doing now is I will now have the solution that I need to use for the bar soap or for the medication, and I just work with that. And all of that number just pour into the something and say, okay, this is the amount of pharma cold and flu or whatever, or Irish Spring or whatever I'm going to be getting. Because you are working backwards now in order to get the number of moles of what it is that you really have or need. All right. So let me recap what it is that we've done right here. So in order to calculate the concentration of sodium hydroxide, that was our aim. Our aim was to calculate the concentration of sodium hydroxide. We don't know the concentration of sodium hydroxide. That is our unknown. But we're going to be reacting sodium hydroxide with our known. And our known is going to be a 0.25 moles per dm cube of sulfuric acid. And more specifically, what it is that we're using is 23 centimeters cube of that 0.25 moles per dm cube of sulfuric acid. Now, based on the titration that we've done, we recognize that we use 25 centimeters cube of our sodium hydroxide. So 23.50 centimeters cube of a 0.25 moles per dm cube sulfuric acid requires 25 centimeters cube of hydrogen sodium hydroxide for neutralization. When I'm saying neutralization, I mean exactly that amount of acid is going to neutralize exactly this amount of base. And once I find that, and I want to find, and I want to find the concentration of my sodium hydroxide, there are several things that I need to do. The first thing I need to do is to see how sodium hydroxide and sulfuric acid react in a balanced equation. So I'm going to be writing my balanced equation, remembering that an acid plus a base gives me salt and water only. I can't just write the formula and just do it like that. I have to make sure it's balanced. So the number of atoms on either side must be equal. So when we look at the sodium hydroxide, we know it's NaOH plus H2SO4 will give me my sodium sulfate, Na2SO4 plus my water. I know that I have 2 moles of sodium on the right-hand side, but based on the equation, I would have had only 1 mole of sodium on the left-hand side. So I have to multiply that by 2, hands down, so that I can get my 2 moles of sodium on the left-hand side and my 2 moles of sodium on the right-hand side. But multiplying this sodium hydroxide by 2 changed the number of oxygen as well as it changed the number of hydrogen. So I have 2 more oxygen on this side, but watch it now. Remember, I have 4 oxygens here, and then now this is multiplying each of these atoms. So it means that I'm going to get 2 oxygen. So I'm going to have 6 oxygens on this side. Let us check how many oxygens I have on the right-hand side. I'm going to have 4 plus 1 from water is 5. That can't work. My equation is not balanced. Can't work. So therefore, since I don't know what to do with that one, I'm going to see if I can move on as we did the last time to our hydrogen. And when we look at our hydrogen, we recognize now that that 2, sorry, that 2 from the sodium hydroxide also gives 2 hydrogens on this side. And the 2 hydrogens would be the 2 hydrogens, along with these 2 hydrogens, will give me 4 hydrogens. So the best thing to do is to multiply here by 2. Once I multiply here by 2, I'll end up with my 4 hydrogens. So I know that my hydrogens are balanced. But hold on, sir. When I multiply here by 2, it means that I've now increased my oxygen by 1 more. So I know I have 2 oxygens plus 4 oxygen. I have 6. What answer I see? 6 oxygens on the right-hand side. I know I have 6 oxygens on the left-hand side. And I look to see if my sulfur is balanced. 1 apiece. So therefore, I am balanced by having 2 moles of my sodium hydroxide reacting with exactly 1 mole of my sulfuric acid. So the mole ratio is going to be 2 to 1. We can't just say 2 to 1. It is two moles of sodium hydroxide reacting with 1 mole of sulfuric acid. Now, remember the aim, is to calculate the concentration of the sodium hydroxide, but we don't have any information about the concentration of about the sodium hydroxide. We're only given information about the sulfuric acid. And we know the information for the sulfuric acid is that 23.50 centimeters cube of that reacted with exactly 0.25 moles per dm cube of the sulfuric acid. So we now need, since we have the mole ratio, we now need to calculate the number of moles of the sodium hydroxide, or unknown, that was reacted. So calculating the number of moles of the sulfuric acid, we are going to say 1,000 centimeters cubed. Sir, why did you start off with 1,000? Because it is moles per dm cube. 1 dm cube is equal to what? Talk to me, no man.
1,000 cmq. 1 dmq is equal to 1,000 cmq.
Very good. So 1 dm cube is going to be equal to 1,000 centimeters cube. So the mere fact that I have 0.25 moles per dm cube, it is saying it's 0.25 moles in each dm cube of the solution. So therefore, I'm starting off by saying 1,000 centimeters cube of my sulfuric acid contains 0.25 moles, which is a true statement. How many moles, what's the volume of sulfuric acid that was used? It was given to me 23.5, don't?
Yes, sir.
So we're going to say, we want to find out what 23.5 contains. Now remember, when I have the tin of Dr. Pepper, and work with me. When I have a tin of Dr. Pepper and I decide that, yo, I'm gonna have only a half a tin, would I have consumed the 150 calories?
No.
I would only consume 75, right? Right, because
Yeah.
only half as much. Good. So this is why when I saw that come in Asia, big back, what we call it? Big back activities. Yeah, I saw that come in. And it was explained to me what big back means recently, so I know exactly what you're talking about. When I buy a pack of water crackers and I'm only having 4 of the water crackers, which is my suggested serving size, it means that I'm within range. But when I'm having 12 of them, oh my goodness, I'm having 3 times my stuff. No, it will have to tell me how many calories are going to be contained per serving of those 4 crackers, water crackers. And then I multiply by 3 to see what my daily value, what I would have already taken in, to know what it is that I can already have. It's the same thing with the solution. I have 0.25. I don't want all of the 0.25. I only want 23 centimeters cube, or 23.5 centimeters cube. Now tell me what 23.5 centimeters cube will account for in the solution. I'm only taking out 23.5 from the 1,000, and that is going to approximate to 0.005875 moles. So the 23.50 centimeters cube of the sulfuric acid is only going to contain 0.005875. Everybody see that? Pause the seat.
Yep, I saw it.
Pause. Asia, you see it?
Yes, sir.
Remember now, I don't know where pause gone, but remember now,
Yes, sir. Yes, sir.
if the Dr. Pepper says the serving size is 150 calories, and I decide that I'm not having a full tin, I'm having a half a tin, will I have consumed 150 calories? Question? Yes, no, maybe so.
Nope.
Right, I wouldn't have. I wouldn't. So just like how we know, so 1,000 centimeters cube of this sulfuric acid contains 0.25. We never use all of it. So therefore, answer can't be more than 0.27, 0.25. It has to be far less because we're not even use 100. We barely use 23, 23.5 we use. So I'm saying this to say to you that your value makes sense, 0.005875. Now, from that, we now calculated the number of moles that reacted, number of moles of sulfuric acid that reacted with the sodium hydroxide. Now, what it is that I need to do, I need to find out now how many moles of the unknown, my sodium hydroxide reacted in the solution. So therefore, I have to go to the balance equation. And I know that 2 moles of the sodium hydroxide reacted with 1 mole of the sulfuric acid. So any amount of moles of sulfuric acid that reacted, I times it by 2 to get the number of moles of the sodium hydroxide. Talk truth.
Correct.
And that's why I multiplied it by 2 here to give me the 0.01175 moles. So this is the number of moles that I know reacted in my sodium hydroxide. And then now if I wanted to calculate the concentration of how concentrated was the solution that I used, I said, okay, fine. I know that this is moles, but I know that this is contained in my 25. So this time I'm going to start off with 25 centimeters cube of my sodium hydroxide contained as 0.01175 moles. But guess what? My solution is always made up in 1,000 dm cube. Now, guess what? When I say always made up, I can make up a 5, I can make up a 0.5. I can use a smaller volumetric flask, right? I can say to you
100.
100. I can say 100 in terms of saying 1,000 centimeters cube. I can say 100. And what is 100? What is 100 centimeters cube in relation to dm?
So that'll be 1/10
1/10 or 0.1 dm cube.
0.1, yeah.
All right. So I say this to you that we still come back to representing it as dm cube. So we know that we use, because we have 100 milliliter volumetric flask. We want to do a small experiment. We just make up a little 100 milliliter. I will make it up, and then chances are we're going to use 23 out of it. So we'll have 70, enough. 76.5 left. And we can say, boy, that can do for something else. Someone else can run another experiment with that. Or I mean, you're able to use it later on in the day instead of wasting the solution, right? So now, when I'm trying to calculate the concentration, I'm going to start off with my 25 because the volume of the sodium hydroxide used was the 25. And that's what it is that we do in order to get the concentration of the sodium hydroxide used in the calculation. Really not difficult, I promise you. Let me just, again, go through the steps. You're going to write your balance equation. Having written the balance equation, then you're going to ascertain your mole ratio. Then you're going to calculate the concentration in moles per dm cube of the known. And then the fourth step is that you're going to be using your balance equation to determine the number of moles in your unknown. And then finally, to calculate the concentration, what it is that you're going to be doing is to say whatever volume was used for the unknown and the number of moles that was just calculated or derived from the mole ratio, and then that's how we calculate the concentration. Easy 1, 2, 3.
Oh, sir.
Yeah.
Something just came to mind. Right, so you added up the 3.
The 16, the 23, and the 1?
Yeah, the mass numbers. And you got 40. However, when you divided the 25 into 1,000, you got 40. Is there any relation at all in that?
Not at all.
Oh, okay.
It's just a mere coincidence. just a mere coincidence to get the same thing. I saw it a while ago when I was doing this stuff. I was like, just look at that coincidence. Now, you know what is so interesting? I spoke to you about relative molecular mass, and then now the second question, did you recognize the second question I have for you now is for you to calculate the relative molecular mass of the sodium hydrogen carbonate. See, RMM?
That was just the mass over RMM.
Right. So the relative molecular mass of the sodium hydroxide is 40 grams per mole. Now, what we need to calculate now is the relative molecular mass of sodium hydrogen carbonate. So guess what? I want you, and that's the other, I'm not going to do the other question. Let's going to stop at this one. I want you to write the formula for me of sodium hydrogen carbonate. I'm going to give you 5 minutes to go and just see if you can write the formulation for me. Sodium hydrogen carbonate. Let me share, no, sodium hydrogen carbonate. What am I sharing? All right. All right. So what I asked you to write for the formula to write for me, sodium hydrogen carbonate. So there's a list of my anions and my cations. I'm not giving you 5 minutes anymore because now I'm giving you the anions and the cations. So look at my anions and cations and write for me the formula in 3 minutes of sodium hydrogen carbonate.
Sir, what if you give with that? We don't need 3 minutes.
What is that again, Mikey?
No, sir, if you give with this, we don't need 3 minutes.
You don't need 3 minutes, I know, but I was just being very generous. All right, so tell me the formula for the sodium hydrogen carbonate now.
NaHCO3.
Agreed, the rest of you?
Yep.
Good job. Use the other 2 minutes now to calculate the relative molecular mass of sodium hydrogen carbonate.
I need more than 2 minutes.
After use up the time, well enough.
Sir, and it's always times 40, right?
You have to be careful of that times 40,
No.
No, it's not. It's not
With
always
regard-
times 40. You remember, 40 is just a coincidence in this case. So
No, I was thinking about the MG
concentration,
over the R, the
RMM,
concentration, yeah.
right? No, it's not times 40. What we're going to do is for the sodium hydrogen carbonate, sodium is 23, hydrogen is 1, carbon is what? 12 or 24?
Carbon, no, 20, carbon is 12.
Right. And then no, oxygen is 16 or 32.
Oxygen is 16.
Good job. So just add up those, and that will be the answer. Simple 1, 2, 3. Compass and gauge, quick and fast.
$52.
Yams or bananas? 52 yams, 52 bananas.
Hold on.
Grams per mole. Grams per mole.
Grams per. Oh,
Mhm.
52 grams per MOLE.
Right. Or you can shorten for MOL, same difference. All right. So that's basically how it is that we'll do one of those calculations. I will reserve other examples until I actually do one of those experiments for you and videotape it and then play it in class and then, tell you exactly what is done. And then we can just go ahead and just mimic us doing the actual calculations. Are there any questions of me at this stage?
No, sir. I am pretty.
Just more practice.
Definitely.
Okay.
Just
All
ensure
right.
study the periodic table, the 20 elements every day.
Yeah.
Study
And
atomic number, protons, and the mass number, and the different elements and the location. And trust me, it becomes a little bit more simpler.
yeah, it does. All right. So with that said, I'm going to give you, all right, we have 90 minutes left. There is an activity that I wanted you to do for me. If only I can find it. I'm going to give you, all right, I'm going to tell you what it is. I'm going to tell you what it is in 2 seconds. Okay, apply the mole concept. Okay, perform acid-base titration, redox titration. Right, I'm going to demonstrate that one. It says apply the mole concept. All right, so what I want you to do for me, I'm going to give you 10 minutes each to define the concept of environmental chemistry and green chemistry. I want you to define the concepts of environmental chemistry and green chemistry. So you're going to do your quick and fast research. I'm dropping what it is that I want you to do in the chat. I'm giving you 10 minutes. Just something, I don't want anything highfalutin that you're going to check off the internet and when you read it to me, you don't know what it is saying. Read it and then, come and explain to me what is the definition of this environmental chemistry and green chemistry, what it is. So I'm giving you 10 minutes for that, starting now. Quick and fast.
Oh, sir, I got disconnected. My laptop died. Did you give the work ethic?
You see it again? I just reposted it.
Yes, sir. Thank you.
Cool.
All right, how is Steve? Who is brave enough to go first?
Yeah. Well, no, I am
All right, so
actually a little. You want to go first?
all right, so I'm gonna tell you what I have. All right, so for environmental chemistry, I said this has to do with the chemical processes within the air, water, and soil. How these chemicals transfer from one area to another, such as air to soil and soil to water. It also has to do with the purpose of these chemicals and how they behave within the environment, as well as how these chemicals interact with human activity. So, what else? My understanding of this as well is that so some of these chemical processes would be like what you call nitrogen, carbon. So all of these are chemical processes, and they take place. Oh, this is coming. And they take place within the different areas of the atmosphere. So the areas, I said, the soil and the water. Give me 1 second, please. Sorry about that. The green chemistry now. Green chemistry is the design of chemical products.
Where you gone? Hello?
Pause.
me?
If you talk.
All right, maybe he got but no, he's still here. Paz, you're muted here.
Sorry. Say again, sir.
Let's say you're muted.
No, I had to answer a call. Somebody was calling me, so I got distracted. Sorry about that. So I'm moving on now to the green chemistry. So the green chemistry is the design of chemical products that reduce or eliminate the use of or generation of hazardous substances. What else did I say about this now? This one was a little bit more difficult for me though than the environmental chemistry to really understand. So that was really what I had. The aim of green chemistry is also to reduce the chemical impact on human health and other living organisms and virtually eliminate the contamination or reduce within the environment. That's what I have, sir.
Good up. Mikey?
Okay, sir. So for me, so environmental chemistry in general is basically studying the chemical processes and in the environment and the effect it has on like ecosystems, human health, and so on. And like focus areas, most of the focus areas are like, as far as would say, pollutant, chemical transformation, and major environmental contaminants or contamination. And in general, basically what they'll do is like study the effect of a particular chemical and how it has impacted the environment. So a good example would be like DDT, when they were using it to spray mosquitoes to get rid of malaria, and then they ended up realizing that hey, this thing bioaccumulates, and then you'll have an issue. Another example would be like industrial runoff, surface runoff from industrial areas, which would deposit like heavy metals in your rivers. Environment, green chemistry now, as part says, basically the design of chemical products to reduce the hazard that they would have on the environment, or the hazardous impact it will have on the environment. And so instead of reacting to the pollution, you try to do like pollution control to prevent the pollution. You try to do renewable resources and employ more like sustainable methods. And one thing that came to mind, and past them wouldn't know about this still, but you used to have like leaded gas, and it was basically added to improve on the octane of the gas. And with green chemistry now, they would have re-looked at how it is refined, upgrade the processes, and they would add other things like benzate which would still give the same effect, but it's safer. So that is my little 2 points on it.
Asia?
I'm sorry, I would say that environmental chemistry basically investigates how pollutants and other chemicals impact ecosystems and human health, and it can help to understand the complex interaction between our environment and the chemicals that are in it or make up it. And for green chemistry, it can prevent pollution at the source by like developing environmental alternatives, sustainable practices, and so to create a more sustainable industry. So like reducing waste and using renewable resources and so. So it's basically the difference between them would basically be chemistry would be studying the impact, and our environmental chemistry would be studying the impact, and then green chemistry would minimize the impact in a sense.
Pretty good. What I want you to do for me over the weekend is to read up more about the environmental chemistry and the green chemistry. One of the things that you need to remember for the environmental chemistry, we look mainly at 3 areas. What are the 3 areas again, Charles?
Air, water, soil.
Air, water, and
Water, soil.
Let me say.
Soil, air,
Right.
water, soil.
Oh, air, water, soil. All right. So air will be atmosphere. Water will be the hydrosphere.
Hydrosphere.
Good. And it's not just soil, but it's land that we're looking at. And land will be the
Lithosphere.
Lithosphere.
Good. So that's where we're moving into now. So, which is why I asked you to look at the environmental chemistry, the green chemistry. So yes, the environmental chemistry is going to be looking at mainly those 3 areas: the atmosphere, the hydrosphere, and the lithosphere. So here goes a reading. So the time that I spent to just get the foundational chemistry aspect out of the way is going to be caught up now by you doing lots of reading, so we can come to class and we can have conversations, right? Now, those 3 areas, the 3 spheres that we're really concerned with environmental chemistry, we have to look at things like pollution. And pollution occurs in all of them. So when we talk about air, what kind of pollution are we talking about? Some
Air
examples.
pollution.
Such as?
Or like smog, smoke.
Smoke, yeah. Acid rain.
Carbon emissions.
Good.
From factories.
Yes, ma'am. And what about and this is one of the things that we're going to come to again. Or cars or motor cars must have things like catalytic converters to them so that it can convert those dangerous sulfates and nitrates into useful gases to reduce the effect of the acid rain buildup in the atmosphere. You see what I'm saying? So we talk about those. We can talk about noise pollution too, Noise pollution is in where? In the atmosphere too, though? Talk to me now.
Yes, sir.
Yeah,
Yes,
we
sir.
can talk about wind pollution, don't? So when we talk about wind pollution,
Yes,
we talk
sir.
about the migration of topsoil from one area to the next, don't?
Yeah,
Yes, sir.
definitely.
Yeah, man. And what happens now is that when you have the removal of these topsoil, you're now exposing the root structure of trees, don't?
Sir, ash would be one as volcanic ash would be one.
Yeah, man.
Yeah, man.
Yes, man. Oh, absolutely. Absolutely. You know? And then now, when we talk about what, and I mean, there are others that we can talk about and the effects of them. We talk about water, we talk about plastics, we talk about, you know, well, it's mainly plastics, but, you know, when we have our trees that we decide that we're going to dump our stuff, you know, into the ocean. For example, some hoteliers decide that, yo, I'm not spending that money to go and call in these cesspool emptiers. I have my secret effluent exchange into the ocean. So when all the hotel people them do them number one and them number two, them just open the valve and just let go all of the feces into the ocean, right? And empty their raw effluents into the ocean. So what it does, think about those aquatic plants and animals eating those stuff, and then man go eat them something. You know, it causes us to be sick as well, and it
But
pollutes the
sir,
ocean. Yeah.
I always like being that you just brought that up, right?
Mm.
Why, I'm just wondering, why on earth would those persons think that that would be a good thing, and only like I think I understand the aspect of where they're coming from, as in they probably think that it's doing them good in terms of like maybe the reduction of costs,
And that's
but
it.
in the long
No,
run
that is
it's
it.
still going to affect them.
But they are not
It's
thinking
still
of the
going to affect
environment.
them.
So it does, but they are so small-sighted and small-minded, because what happens is, maybe to call in cesspool emptier to come and clear the stuff. Maybe they're going to use like all, because it's commercial, it's going to be different from the residential price. So what you pay, you may draw a load for $20,000, or I say $30,000. But because it's commercial, they may draw a load for $100,000. And because they're going to draw several loads, 10 loads, them say, but we can't pay $1 million to do this. No, we're going to just empty the effluents into the oceans. But what I want you to look at for me is policy. When they empty that and the policy come and say, okay, we're charging you $100,000 for polluting the environment, they're going to pollute the environment and pay the $1,000 because them still save $900,000. You follow what I'm saying?
Yes, sir.
So it's not just hoteliers. In recent times, and I know we're finished, but in 2 more minutes, in recent times, places like True Juice, they're emptying their effluents into the Rio Cobre. And every time they're doing this, they're saying that, oh, it's a breach in their pipeline. It's no blinking breach. It is deliberate. And sometimes they do this because it is saving them, because when they do this, they say, okay, fine, we will clean it up. So them go to NEPA and say, no man, we'll clean it up, or environmental people are on top of it, because it is costing them less to clean up than to have the people them coming to empty their effluents. All right? And what it does, it kills aquatic plants and animals. Sometimes when you're driving past Mandela, you can't even hold your breath because of the stench, dead fish. And then you know what is happening? When the fish them dead, the man them decide, say, yo, they're gonna make a money, you know, and they're gonna buy the dead fish. Sorry, not buy, but they're gonna collect the dead fish and come and sell you. So it has implication to man. And then, so we talk about air, we talk about water and land. When we empty our effluents, when we empty our stuff on land, it causes a whole lot of problems. Or lead batteries gets leached into the soil, causes problems. We burn, causes problems. So one affects the other, because when we burn on land, the smoke gets into the atmosphere, causes pollution there as well. And then now what happens is that the effluents from the burning also falls into the ocean. It gets swept down. These aquatic animals eat them, they die. So life is just a cycle, which is what it is that we're talking about. It's just a cycle.
Answer.
Yeah.
You know, right out, well, not necessarily airport, but like on Palisado Strip. I don't know if you guys passed there recently, or how long it has been happening, but the stench there, so sir, Jesus and peace of mercy. I don't know. I'm really wondering if it's effluent that is being emptied out into the harbor. And I'm wondering because they also had like some apartments there that had been recently built. I think probably like a year or two ago.
Oh, that's on the
I'm
left
wondering
hand.
if that is a built
That is
into
close
it.
to the gas
The
station.
roundabout.
The roundabout by the gas station, right
Yeah.
beside the gas
Yeah.
station there, on the left hand side going to the roundabout.
Yep.
Yeah, it is possible because I think across from there is Marina Villa or something of the sort. It could be because we now need to check National Water Commission to find out exactly how the piping system work, because over there was just land, and all of a sudden you have big complex over there. So we
And
don't know. Go ahead.
At one point as well, there was sewage going out onto the road.
Absolutely.
Onto the road, and I think National Works Agency, they had to because I think the pipe under the road, it burst. So it's like you have to wind up your window because you know nobody splash you with the water. It was literally on top of the road. So
Yeah.
I mean, I'm just wondering if I'm really just really curious. I'm wondering like how there's nobody in charge, no environmentalists,
There
or
are
at
people
least
in
never
charge, but people are
drive
not
past
doing
and
their
smell it.
jobs. People are in charge, people are not doing their jobs because people are being paid off. And which is why we want you to go out there and get into policy so you can make these changes. So I'm saying to you, one of the things that I want you to also look at and be mindful of when you're doing your readings is BOD and COD. I'm not telling you what those are. BOD levels and the COD levels. Because I'm sure if they were to go and check the BOD and COD levels in that section of the harbor paths on the right-hand side going to Harbor View, the readings are going to be alarming. The readings are going to be alarming. So I'm telling you, when you guys finish Asia, you need to leave down on North Street. Paz, you need to leave Palisados. Well, Mikey did this so. And Carol need to leave where she did. And we need to get into policy. You need to get into NEPA to work to change some of these things. Because it is also damaging, we call it. It is also damaging man's livelihood, because man go over the side of the right-hand side for go catch fish in our pass. So I don't know if you ever pass them
I
one
see
time, I
them
see them
with the boats.
with the boat. Absolutely, absolutely. So you know, it is very concerning what is happening. And this is why on your exam paper you get scenarios, and it will happen for engineering, environmental engineering. It will also happen for wastewater management, for environmental chemistry. The pollution is something very serious. Michael started with the deed, the fogging. They recognize that what it is that we're using was very harmful to man's health. So they know how to go and use some green chemistry to make it safer for people to breathe, because people who have respiratory illnesses. So instead of killing the mosquitoes, it was really killing us. So they have to find ways of mitigating the damage to the environment, so it is that man can be safer. So it gets interesting. That's the point I'm making. So I'm going to end here. What you need to do is to read, don't stop reading. We need to read about the atmosphere. We need to read about the hydrosphere, the lithosphere, and we need to have an understanding, a clear understanding as to what happens. Let us spend some time on pollution. How things are polluted, you don't know. You can get pollution for the atmosphere, lithosphere, hydrosphere, or you can get a question that infuse all three. You need to explain yourself and let them know, so boy, you are an environmentalist coming up to do X, Y, Z. All right? Pick up yourself. We'll talk.
All right, sir. Later.
Okay, great weekend.
Like that.
Mama.